All right, welcome back to another edition of our Liftoff webinar series. My name is Joe Steele. I'm the Senior Director of Communications and Legislative Affairs here with Lyft in Detroit. Thank you so much for taking time to join us today. Today, we're happy to welcome the Aluminum Extruders Council. Mark Butterfield will talk to us about the benefits of using hollow aluminum extrusions to meet some of the engineering challenges that folks might face. But I do have some housekeeping issues I'd like to take care of first before we hand the presentation over to Mark. Everyone should be muted. If you're not muted, please go ahead and do so. We are recording this presentation and would like to avoid as much background noise as possible. So again, you should be muted, but if you're not, please go ahead and do that. We are recording this and we'll post it on our Lyft website at lyft.technology in the next 24 to 48 hours. So you can revisit it there or share it with folks who are unable to join us today. Also, we will have a question and answer session after the presentation. So please use the Q&A function that's on the Zoom toolbar. Try to avoid the chat function, use the Q&A function. We're all very familiar with Zoom and other virtual tools after the last 2 years. But go ahead and use the Q&A function. We'll facilitate that Q&A afterwards. So you can go ahead and ask them throughout, but we'll address all of them afterwards, even if it relates to something earlier in the presentation. Again, my name is Joe Steele with Lyft, and I do want to give you a couple of minutes, a little bit about Lyft, in case you're unfamiliar with who we are and what we do. We are a nonprofit public-private partnership and national manufacturing innovation institute based here in Detroit. And our goal is to drive American manufacturing into the future through technology and talent development. We know that on the future, or on advanced manufacturing, rests the future of our economic security and resiliency and national security, to be honest. So we know that the next area that tackles and masters advanced manufacturing first is going to come out ahead. And as a Department of Defense sponsored manufacturing innovation institute, we want that to be the USA. So what do we mean with what we do and how do we do that? Well, we call it solving the manufacturing equation. We live at the intersection of material science, manufacturing process, systems engineering, and the talent that rides underneath all of those. We want to make sure that we know that the characteristics of the materials that we're working on for what we need to build today and in the future. We need to know how they're going to react based on whatever process they're going to be put through, and understanding that those materials characteristics after that manufacturing process will help us understand if they're fit for purpose for whatever system they are going to, those components and parts and pieces are going to end up in. We also want to make sure that we have enough talent in the advanced manufacturing sector in this country to move the needle forward as well. So really, we operate that with two business units here at Lyft, two programs at Lyft. Our technology program, Leading Innovations for Tomorrow, and our talent program is Learning Innovations for Tomorrow. So a little bit about the talent or the technology program, Leading Innovations for Tomorrow. It's about connecting materials, processes, and systems. All of our projects, technology innovation projects, work and fall under these 4 buckets. We're really trying to take ideas and innovations, move them across the valley of death from MRL, say 4 into MRL 7, so that they can be commercialized and put in the hands of industry and the warfighter as quickly as possible. So you can see everything from the digital side, integrated computational materials engineering, where we're looking at materials in the virtual space, understanding how they'll react, how they'll be processed, see if we can predict how they will react and how they'll after the processing, and better understand that in the virtual space, so we don't live in a make it and break it world, and we can actually know what is going to happen before we have to actually physically make things. But we are physically making things, and you see that in the advanced alloy and process development, as well as the agile and smarter manufacturing, working in things like lightweight armor development and hypersonics materials, processes like wire arc additive manufacturing, cold spray additive manufacturing, working on all these things, better understand the materials and their characteristics moving forward. And finally, if we're using all these new materials, how are we going to join them together? What can we do to join all these materials together so they get along and play nicely together, and they're also fit for whatever purpose they need to serve. So that is what our technology team is working on here in Detroit and across our ecosystem each and every day. On the talent side of the equation, still about innovation, but this time we're talking about new tools, new pathways, new venues. Really starts with our LIFT Learning Lab that is here in our Detroit facility. It is a unique immersive lab where we're able to test out new curriculum, give students an exposure to what advanced manufacturing looks like in the year 2022, and prepares teachers actually for what they can be and should be teaching students going forward. Really take a look at the innovations that are taking place. So that really revolves around our Ignite Mastering Manufacturing curriculum. That is a 3-year curriculum for high school students. We teach it out of our Detroit Learning Lab, but it's available in about 10 states and about 35 schools around the country right now. It's a 3-year program giving students some foundational experience in all kinds of different manufacturing, including material science, including advanced manufacturing systems. So we're looking forward to rolling that out even further around the country moving forward. For our more adult learners and folks that are ready for jobs that are available now and today, we offer our LIFT certified program as well as a program called Operation Next. Both teach the same 4 majors, which are CNC machining, welding, industrial technology, maintenance, and robotics. Those first 3 majors are the most in-demand jobs for today, and robotics is the fastest growing. So we have programming available at our LIFT headquarters. So if you know folks that need to be upskilled, need to learn a new skill, interested in starting a new career in advanced manufacturing, give us a call. We'd be happy to help them. If you have people in your organization that need to be trained, give us a call. We can work with you on that as well. Most of our training is free of charge, funded in some way, shape, or form through the federal government, state government, local government. We have funding sources for them to give people an opportunity to move into advanced manufacturing careers. I will touch on Operation Next really quick. That is a program designed for our military members, people who have served our country so bravely, both active duty right before they separate from their service, as well as the Guard and Reserve, and their family members. Give them an opportunity to start their civilian career with a nationally portable, industry recognized credential. That is available in about 9 or 10 different locations around the country, including our Detroit facility, rolling it out in Virginia, Kentucky, Alabama, New York, Wisconsin, all various number of places around the country. You can check that out on our website as well. Wanted to do what we could to give back to our service members and get them started on their next career, their civilian career. So I mentioned we are a nonprofit public-private partnership. We're also a membership-based organization. These are things you can expect as a LIFT member. We're again, trusted advisor. We're Switzerland, as we like to say. We're not selling a particular product or service, just trying to give people the best advice we can to move them forward into advanced manufacturing, including digitalization, smarter manufacturing. A technology accelerator, as I mentioned, taking those good ideas, moving them across the valley of death into commercialization as quickly as possible. A technology showcase, and actually showcase and sandbox here in our Detroit facility, 100,000 square foot facility, $50 million worth of equipment to work on, design, prototyping, and also show the art of the possible. What is coming down the road in advanced manufacturing. We're a connector and a convener. Thank you so much for joining us today. Glad to bring the best and brightest minds together. So we'll hand it off to Mark in just a second. Talent developer, I touched on that all the way from high school students to learners and soon to be veterans, trying to get folks exposed to and into advanced manufacturing careers. And finally, as a Department of Defense Manufacturing Innovation Institute, we are a government partner. It can be tricky to start to work with the federal government. It is a big place, particularly for our small to medium-sized companies. So we serve as a conduit to do just that and help folks take those ideas to the DoD and other places. So appreciate you taking the time to join us today. You can follow us on any of our social channels. You can shoot us an email, give us a call, visit us on our website to learn more. Be happy to talk to you more about LIFT. But in the meantime, I'm going to hand over to Mark to talk about the benefits of hollow extrusions, which is really why you came here today. So Mark, I'm going to hand the presentation off to you, and the show is yours, sir.
Thank you, Joe. And just get my screen up here.
Looks good.
Okay, Joe, thank you for the overview of Lyft and the programs that Lyft offers. Tremendous organization, tremendous program. We've taken advantage of that ourselves, so a lot of opportunities there. So I'm glad and excited to be talking to everyone today. Thank you for joining and spending the next hour for our webinar. I could talk to you all day for this. But fortunately, we're just going to spend an hour here. But we're going to talk about the power of utilizing hollow aluminum extrusions to meet some of the demanding challenges, engineering challenges, product performance requirements that we're seeing in the industry. But first, a little bit about the AEC, Aluminum Extruders Council, the industry association for North American extruders. We represent a little over 60 extruder members, accounting for greater than 80% of the extrusions produced in North America. The organization focuses primarily on user education, member excellence, and fair trade. A tremendous organization. I would encourage everyone to take a look at the website, www.aec.org. Again, tremendous organization that supports the extrusion industry in North America. A little bit about my company, Pennex Aluminum, a longstanding AEC member with casting capabilities as well as advanced extrusion, fabrication, and assembly operations, both in Ohio and Pennsylvania, and a leading supplier of custom extrusions, fabricated components for the automotive applications, as well as other markets demanding more advanced aluminum solutions. So now today's agenda, we're going to cover three areas. One is design consideration with aluminum extrusions. The other is solutions with extruded hollows. We've got some examples of how hollow extrusions have been utilized in the past, and then achieving the desired result. So three key areas of the presentation. But first, designing with extrusions. So designers can join the outstanding characteristics of aluminum with the unique attributes of the extrusion process. So with aluminum, just to highlight a few that we utilize and that stand out early on is the lightweight, the high strength to weight ratio, corrosion resistance, and heat conductive for thermal applications. If you just take those four and combine it with the benefits of the extrusion process itself, we can tailor the performance. We can put the metal where it's needed. It's unique to the extrusion process. It's very suitable for complex integral shapes produced to very close tolerances. Easy to fabricate and joinable by various methods. Cost effective and very short production lead times and tool costs. And in today's world, moving quicker, faster, and more cost effective is certainly at the top of the list. And in addition to it, and we'll have a couple slides, fully recyclable and sustainable product. So taking into consideration the aluminum, the characteristics of it with the attributes of the extrusion process, there's no wonder why extrusions have taken off, not only in the automotive market, but other markets as well. So starting first with alloy. So as of June of 2022, there were over 564 alloys registered with the Aluminum Association. And I will note that this does not include proprietary alloy variants. I would say that this number triples when you start looking at specific alloys that have been developed that are proprietary to either raw material suppliers or extruders themselves that have their own casting capabilities. And the reason we see so many different alloys within the different series is because the alloy is the foundation that we work from. That's where our product performance is going to come from. And it's also a significant cost driver relative to the product, and also has an impact on the tolerances that are capable. So we have to take all three of those into consideration when we're choosing the appropriate alloy. We're going to focus on today 6000 series, which you can see there's 110 registered alloys within 6000 series. Again, when you start to look at some of the proprietary alloys, that probably triples, if not more. 6000 series is the mag silicon-based alloy, and a heat treatable alloy at that. So one thing to look at, and where I always like to start, is understanding that any one given alloy can have a lot of variation to the formula itself and can be tweaked to optimize its properties. And for me, this is one of the most critical slides that you look at and that you want to understand when you're going into your design and your development, because as you can see, and we're looking at silicon and magnesium here, but you can see that there's overlap between 6082, 6005, 6061, and even 6060 overlaps with 6005A. But the difference relative to these chemistries are significant for lots of other reasons. One, as we rise in silicon and mag, we also decrease our extrudability, so costs rise. As we increase in both elements, we also demand a higher or more aggressive quench rate that can have a negative impact on tolerances as a result of the distortion during the quench process itself. So understanding the overlap and understanding specifically where your product needs to lie relative to a specific chemistry is a significant starting point. As we see with 6082, which tends to drive a higher billet premium, we have additional costs there where we may be able to utilize a 6005 alloy, little less cost, little less quench sensitive, may drive a little bit better tolerance. But all alloys have their place. And within these alloys, there's significant variations. Again, not only because of the chemistry, but as we'll talk further into the presentation, the homogenization and the processes associated with them. You can kind of see some of the applications that are utilized within these bands: intrusion beams, bumper beams, more structural auto chassis tend to be in the 6082, 6005, 6008 alloy, which lies right in that 6005 range with some additional vanadium added to that. And then when we get into the 6060, 6063, we start to see more of the auto trim, heat sinks, electronics, less structural applications. So the foundation that we tend to work from here is this chart. When we look, as I talked before, we get into 7000 series as we go up in tensile and yield with the 7000 series, and then we come down the chart from 6082, 6005 all the way down to 3003. You can see we fall off on strength, but if you look at the bottom on the extrudability index, that lower strength tends to drive a lower cost for extrusion. So what we want to do ideally is we want the lower cost extrudability or the enhanced extrudability of an alloy, but get the product performance needs met with a specific chemistry. And that's what we're going to talk a little bit further about. And one way to offset that, and we have a case example of some work that we had done with Lotus, is we want to offset the limitations of a specific alloy by utilizing the geometry of an extrusion for the offset. So in today's industry, the extrusion industry, the type of presses and equipment that are out there, the technology that lies within the extrusion dies, the complexity of hollows and what can be produced is significant. So what we want to do is we want to try to, looking at that back slide, that last slide, we want to improve our extrudability and again, lower our costs, both in extrusion costs and in billet premiums with those higher alloys like 6082, and still meet our performance needs. And one way is with that geometry. So here's an example for Lotus. And you can see a lot of the structural applications. These would be all defined as structural applications as far as the front subframe, the chassis, the extrusions that are within the tub. The first thing we typically think about for an alloy on that is historically would have been 6082, maybe some 6061, maybe in today's world, some 6005, even some 6008. But here's where we were able to take extruded profiles, add some complexity to the hollows themselves, and actually produce these extrusions in 6060 versus the higher strength 6082. The advantages that we get is higher extrudability, lower premium cost relative to the material. But more importantly, and what we're seeing in structures today is the ability to assemble, tighter profile of a surface tolerances that allow us to take care of the assemblies of these more complex structures. So here's some of the profiles. Now this was done a few years back. So in today's extrusion world, these profiles would be what I would consider to be fairly simple profiles compared to what's being extruded. We're seeing extrusion profiles with 18 to 20 hollows. And again, like we started off with, allows us to put the material where we need it and where it's going to have the most value relative to the performance of the product. So it minimizes cost and becomes a more efficient extruded solution. So extrusion-based part properties and performance is driven by geometry, chemistry, alloy, microstructure. And then the way that we achieve that is how we produce it. So it's the structure of the raw material that extruder brings in. It's the extrusion process that's utilized to produce it, the tool design that's utilized, and the metal flow characteristics within that die, the quench, and then the aging process. So it's significant and it's specific. This all begins as we started off with the alloy and making sure we have the foundation chemistry that's appropriate for the product. Okay, so some solutions with extruded hollows. Just a little terminology. Obviously, a solid is a solid profile with no hollow. A semi-hollow is represented there. There's a class 1, class 2. A semi-hollow is defined relative to the area of the semi-hollow compared to the opening, the space at the bottom. Class 2 is simply a non-symmetrical semi-hollow. And then we have defined hollows as class 1, class 2, and class 3. So with strength and light weighting, crush resistance leading to substantial growth per vehicle, we're going to continue to see this. My experience has been this is growing as users are understanding what can be done with an extrusion, both with product performance, but also with tolerances and the efficiencies that can be gained by utilizing aluminum extrusions, and where it makes sense to utilize an extrusion in that process versus maybe another material. We're going to continue to see this growth in the industry, I believe, and I think it's going to become exponential. Again, I think in the industry, we're starting to see more end users better understanding those opportunities, and that's why we're here today, is to try to provide as much information as possible for you to potentially take away from. So crash management, crush cans, significant part of automotive today, saves a tremendous amount of lives. But for safer vehicles, we need to consistently be able to get from an extruded can to a crush can that is predefined, understood, and predictive. So in this case, we utilized the chemistry, the process, the tool design, and then obviously the process itself. Battery boxes, we're seeing a lot of activity in the market with battery boxes for good reason. The crash energy absorption is critical, and it's understood. Torsional stiffness, high strength with minimal weight, and leak-free fluid transfer. Also, the ability to assemble these structures is probably one of the most significant parts of whether or not a battery tray can effectively be produced out of extrusions. As we see, these are very complex extrusions, and they're very complex assemblies. So, looking back at the alloys, when we talked about those, a 6082, for example, a rail of these lengths, a 6082 alloy is going to require a fairly aggressive quench rate. That quench rate is going to cause some distortion, some twist bow, cross-sectional distortion in order to achieve the properties of those specific alloys. But if we can look at another alloy, maybe we're looking at a 6005A, or we're looking at a 6008, or we're looking at a variant of 6082, we can still maintain the product performance requirements for the tray itself, but we can achieve much tighter tolerances. And for anyone who's assembling these types of structures, that's absolutely critical in an automated system. Roof bows, a lot of different applications for this. Typically multi-hollow, torsional stiffness is critical. Lower weight means a lower center of gravity for the vehicle. And these extrusions are achieved over long length and typically bent and formed appropriately for the cab. Rockers, another significant increase in volume. Rocker structures, weight efficiencies for crash management within a steel structure. So there where we see the Tesla 3 rocker structure, it's a good example of where we've used strategic use of aluminum extrusions and the aluminum extrusion process, specifically where it adds value to the structure of the vehicle, and then applying steel. So a multi-material, multi-process approach that provided the solution specifically for the Tesla 3. The Ford F-150 rocker structure, very tight tolerances, very tight profile surface tolerances, multi-hollow, so very strategic in the cross-sectional design for its application, adding additional value to the product. And the extrusions are achieved in long lengths. So no limit to the length of the rockers themselves. And then the BMW i3 rocker structure that we see here, I think really represents the capabilities of our industry today. Not only is it an unbalanced cross-sectional profile, but multi-hollow, very tight tolerance, and provides a tremendous amount of value, and very structural extrusion itself. So very, very efficient use of the material. And as we mentioned earlier, very short lead times and very inexpensive tooling associated with those types of those products. Chassis floor. This is an example of a Mercedes-Benz floor structure. These are 3 multi-void hollows that are joined very efficiently, effectively with friction stir welding. Friction stir welding is becoming more and more common as we start to go to larger and larger applications utilizing extrusions. There's a lot of different size presses out there in the industry. Here you can see these are very large extrusions to begin with, but the friction stir weld process allows our industry to expand beyond that. Very thin walls. We got walls down to 40 thousandths and some variations from 50 to 70, but very, very thin wall capabilities. There's a misunderstanding, I think, in the industry that wall thicknesses need to be up in the 100,000 to 200 thousandths range. But again, that's dependent upon the type of press that's being utilized, the alloy, and the material flow paths and complexity of the hollows themselves. But this was designed for weight reduction and increased capping space. So a good example of a large extrusion utilizing the friction stir welding process in an effective way. Thermal management. This is a great application, a near net shape with minimal secondary machining on the ends, creating a motor housing for truck bus application. Large 250 horsepower electric drive motor that has the 4 mounts. It has the cooling chambers in it. Also, the cooling chambers has additional serrations So the serrations adds to internal perimeter surface, which helps the thermal conductivity and the thermal attributes of the product. So a good application of extrusion. These are made in all different sizes, from very small. We can see here it has an ID of just over 5 inches, but these can go very large, above 12 to 14 inches in diameter has been my experience. Thermal management, just a couple examples here, but thermal management, there's a lot of significant applications, especially in LED lighting that we see on the right. That part is basically extruded, cut to length, and a completed component, and a multi-hollow at that, and a 10-to-1 fin ratios. Now, all extruders have a different ratio that they utilize. Some of that is relative to their tooling technology and their press capabilities, and the type of press, direct or indirect presses, can change those ratios. But in today's with today's technology, we can see ratios even much higher than 10-to-1. The example that we have here is a 21 void hollow, so it just gives you an understanding of where we've came from a technical standpoint with extrusion dies and extrusion presses and the process controls needed or required to produce such a complex part. So now, achieving the desired result, as we mentioned, it's the geometry of the profile. It's certainly the alloy and the characteristics of the alloy, but it's also the process that's utilized. And what we're looking for, as we design the profiles, the cross-sectional profiles, and we apply the different alloys and we develop the alloys. We're looking for our material strength, so TY and E obviously is where we start. The response to processing, a lot of the profiles we saw, formability, bendability, the ability to heat treat specifically to a certain temper is absolutely critical. Yield bands are obviously very critical relative to crush cans and crush management applications that require predictive control of a crush and energy absorption. Surface characteristics, we're seeing more and more requirements relative to corrosion resistance, adhesion, and surface finish. Joinability, as we saw earlier, we need to be able to join these profiles together, but not only join aluminum profiles, but we have to be able to utilize multi-material. So the ability to join not only aluminum, but steel, plastics, carbon fiber. Machinability, the effective and efficiency associated with milling, drilling, cutting, punching, and then obviously tolerances to be able to support the design. Okay, so extrusion-based part properties and performance is driven by geometry, chemistry, alloy, and then microstructure. We talked a little bit about how we achieve that by the raw material itself, the process, the tool design, quench, and aging. So here's some examples, a lot of different profiles, and a little bit about some different alloys that can be used. Historically, I've seen applications, complex assemblies, all with the same alloy, same temper. And for when I first see that, the first thing I think is maybe there's some inefficiencies relative to the use of the alloys, because every alloy has a different characteristic that can be utilized for a different need, product performance need. So here's some examples where an assembly, an engine cradle assembly, has used 61, 60, 63. There's also some 6005 in there. And then there's also different tempers, all utilized as part of the design and the crash characteristics of that cradle. So what do we want? So everyone says, okay, I want alloy. I want to specify alloy, temper, and properties and microstructure. But you're really not looking for alloy. You're not really looking for temper. What you're really looking for is the properties and the microstructure that comes from the alloys and the tempers. So we're going to kind of dive into this just a little bit. So considerations for microstructure. Microstructure affects mechanical properties, the formability, corrosion, weldability, and fracture resistance. And when we think about today's applications, those are the first things that we're thinking about, especially with some of these complex structures that are being extruded today. Grain size, grain geometry, structure, second phase particles, etc. And microstructure depends on alloy composition and the extrusion process that's utilized to produce it. So as we talked earlier when we began, not only is it the alloy, but just as importantly, it's the process in which the product is produced that becomes most critical. One thing that I've ran into, and just speaking with customers in the past, is we can start off with an alloy, and in this case 6082. When we looked at 6082, it was a fairly large band, had some overlap. If you were to look at that alloy, you would see some overlap from 61, 6008, 6005. So first we're looking at the chemistry itself, but then we also need to understand what type of a grain structure are we looking for. So here's an example of 3 different homogenization cycles with slight variations of manganese and the impact that it has relative to the structure of the product. Now, each one of those is going to have different characteristics relative to its performance. So for example, we're looking down in the bottom left corner, we're seeing a fully fibrous grain, going to have high fracture resistance, good intergranular corrosion resistance, versus a recrystallized grain at the top. Doesn't mean one or the other meets your needs, but understanding which one is most critical, because the difference in cost is significant. So the top right, recrystallized grain versus the fully fibrous grain that requires a different chemistry and a different homogenization extrudes considerably different. So the production of a fully fibrous grain is more complex, slower, more costly than the grain structure we see in the upper right. And that changes relative to the complexity of the material flow within the extrusion dies themselves. So the more complex the hollow, the more complex material flow paths within the extrusion dies themselves, and relative to the reduction ratio of the presses, it can change the cost impact that one grain structure may have over another. But this is one area that I see a gap of understanding and can have a significant impact and an opportunity relative to cost, and not only cost, but also product performance. So converting aluminum billet into an extruded component that meets performance specification requires a complex thermomechanical process. So what we do is we take a billet, we take it through a furnace, billet furnace that can either be gas or an infrared oven. Then we put it into a press, all different size presses and diameters, the billets that they produce. We typically take the cross section of the profile and align that to what's called a reduction ratio, and then we can size a press to that. But the proper metal temperature through the die is required to put alloying elements into solution. So the key thing that we're looking for is, what is the input temperature of that billet? How much temperature are we going to develop or rise in temperature through the deformation process? And are we going to yield an exit temperature that's appropriate for that alloy in the quench process that's required? The next phase, and this is what I consider one of the most complex parts of extruding, a more advanced extrusion that's highly engineered relative to its chemistry and tolerances, is the proper cooling. So if we want to put the mag silicon in solution, we want to do that as aggressively as possible with a quench, but we need to avoid the distortion. So the main objective here is we need to quench fast to avoid undesirable concentration of alloying elements and achieve desired hardness, yet slow enough to minimize residual stresses and distortion. Now, a lot can be done in this area, but this is one of the main reasons why the development of a specific alloy or chemistry is so critical, because we can adjust or we can modify the quenching process relative to those specific chemistries and help minimize the distortion while maintaining the product performance needs the product requires. And then finally, proper aging through the aging oven to fine tune those final properties. So the thermal process is critical, as you can see, and kind of what we just talked through. It goes through a lot of variation, a lot of heating and cooling. The first phase there we see is the heating of the billet. Then the extrusion process that generates a rise in temperature within the product that's engineered and required relative to meet the material properties. Then we go through a quenching process. We're trying to get through that critical temperature range in respect to the precipitation of the Mg2Si. Then we get below around 482, we cool off, and that completes the extrusion cycle. We then go through a secondary process for T5, T6, T7 conditions, where we go through an aging process that can get into the range of 340 to 370 degrees Fahrenheit for approximately 5 hours. Now, all of these temperatures and all of these times vary considerably relative to the product, the alloy, and the specific requirements and specifications. So we talked a little bit about geometry, a little bit about chemistry, and a little bit about microstructure. We kind of talked a little bit about the homogenization, the extrusion process, tool design, the metal flow that occurs in the tool, quench, and aging. So here's a very simple case study. This is an application of a bumper. Typically, this may be how we may receive a print. Very straightforward cross-sectional dimensions, pretty basic information, material 6063 T6. So when I see a print like that, there's a lot of questions I have is, we talked about grain structure earlier. What is the grain size? Is there a requirement? Is there a specification relative to the recrystallized layer? For example, is it fully fibrous with a 20% layer? Weld line locations. Is there an understanding of the weld lines, the seam welds that are in the extrusion die itself? And is there an impact to that relative to the secondary processes? So for example, your post-weld locations, what we don't want to do is start a post-weld on or end on a seam weld within the extrusion. So understanding that up front is just an additional benefit. Seam welds can typically be moved around within an extrusion profile, but it needs to be understood up front. Post-manufacturing, alloy, the quench requirement, twist and bow. That's where we need to really understand, what's the post-manufacturing, what type of assembly is going to occur, is welding going to take place? Therefore, we can start to understand what twist and bow would be acceptable. We can reverse that back into a quench that's going to be required, and then that'll kind of help us drive into the alloy. Runout surface, geometry, yield bands, intergranular corrosion. These are just some things that we want to take advantage of understanding during this phase of the design. Because again, a lot of these can be changes made that have no impact to cost, but have a significant impact in a positive way to the performance of the product, and it helps mitigate downstream risk relative to post-manufacturing or post-extrusion processes. So just some adjustments here. We kind of specify the weld surface. We specify areas where there's no die welds. We put some controls relative to parallelism and flatness and perpendicularity. We apply some twist and bow tolerances, make an adjustment in the alloy, add a yield band. So for the 6082, we get some strength, machinability, better fracture resistance. We get the fibrous grain structure, which helps us in our corrosion and our fracture resistance. And then our processing path would be to quench, take it to a T6 temper, and utilize precision AAA tolerances. So the case examples, the results is a tighter yield band with better predictive performance with that tight yield band applied. Specified grain structure and performance, so we get better fracture resistance and better IGC. Better manufacturability, repeatability, and reduced costs, so less total value stream costs. So sometimes you may see a little bit of an elevated extrusion cost, but the ultimate component cost, or once we look at the total value stream, may actually be much more efficient by reducing some of those post-extrusion processes. Tighter geometry control, so twist, bow, squareness. We've taken that in consideration with the quench. Understood where the post welding locations are, so surface condition and seam welds are being considered, and engineered weld locations relative to high stress conditions based on prior simulations of the design. So just some quick benefits of just taking the time to review a design and incorporating the benefits of an extrusion up front. Now, a little bit about the sustainability. As we mentioned, it's fully recyclable. Aluminum extrusions can and are recycled over and over again. Recycling only requires about 8% of the energy necessary to produce virgin aluminum. So very efficient process. Very mature, established recycling infrastructure exists today. It happens every day in all plants. And extrusions can contain as much as 80% of recycled content. So a lot of the product, whether it be engineered scrap from the extrusion process itself or scrap within post-manufacturing, can all be recycled in. And it's key to aluminum extrusion's low carbon footprints. There was a study that I was looking at yesterday. It shows 91% aluminum in autos is recycled at end of life, and as is 95% of aluminum in buildings. So pretty positive and numbers there to consider when utilizing different types of materials. There's some questions about what recycled content is. So when we're putting aluminum or recycled aluminum into our extrusions, and we're not talking about beverage cans, sidings, gutters, engine blocks. We're talking about recycled content that comes directly from the extrusion process. It's part of the engineered scrap of the extrusion itself, and or downstream post-manufacturing or post-extrusion manufacturing. So very clean scrap, and it's isolated relative to the chemistries. So a very controlled process relative to the recycling of the material. So just in conclusion, aluminum extrusions will continue to play an increasing role in many future industrial and automotive solutions. We're seeing that increase. Complex multi-void hollows often facilitate effective solutions with more cost-effective and forgiving alloys. So what we're seeing is the ability to utilize these complex hollows in applications and offsetting some of the alloys that traditionally have been used. And we're seeing that more and more within the industry. And North American extruders are committed to supporting effective use of extrusions. So tremendous amount of new presses going in North America to be able to support the demand that we're seeing as an industry. So the industry is responding to the additional demand that we're seeing, and will be there to support those needs. My largest advice, best advice, is get a very qualified, experienced extruder involved very early on that can support your market segments, and every market is a little different. So a building and construction market may be a little different than an automotive market. Some extrusion presses are set up for structural applications. Some are set up for aesthetics. There's different types of presses, different types of handling systems, different types of operations, but there's certainly operations out there to be able to support your needs, whatever they may be. One thing that I'd like to to note is some work that we've done within the AEC and putting together, you can go to www.aec.org, but it's really an interactive screen that you can go into and you can look at the different automotive applications. So what you can do is you can click on rockers or cross members, roof headers. You go into that area. It'll show examples of how extrusions have been used for those applications, has some case studies, talks a little bit about the properties, the alloys, and some of the characteristics to consider in those areas. So I would encourage everyone to visit www.aec.org. I'd like to thank some of the members of the automotive team. You can see the different companies that are represented there, all of which that support from an automotive standpoint, and also other applications as well, and other market segments. Our larger group, to all the AEC extruder and non-extruder members that are out there and that support the organization. And with that said, I think I'll open it up. I think we have a few minutes for maybe any questions that may be out there.
Yeah, we do, Mark, and thank you very much. I encourage folks to reach out directly to Mark with any questions, and reach out to the AEC for any additional questions and information as well. We have a few minutes for a couple of questions that came in, Mark, and we'll just hit the ground running if that's okay with you. In vacuum die castings, there seems to be a huge emphasis on non-heat treated aluminum alloys, specifically to avoid costs associated with processing and straightening. And is that an area of focus for extrusions as well?
Yeah, I mean, I'm probably not the expert to talk to relative to the casting alloys. The casting that we do is our own raw material that's utilized in the extrusion presses themselves.
All right, we can certainly follow up with that question for a little more specificity afterwards. Talking about the rockers that were discussed, 6082 is significantly higher in tensile strength than 6063. Does that make it more difficult for self-piercing riveting?
No, machinability relative to 6082 is very good. Because of the characteristics of 6082 versus a 6063. So no concerns or issues there.
All right. Can you talk about, you mentioned friction stir welding. Can you talk about that a little bit more in combining extrusions? Is there a lot of excess material required when adding friction stir welding to the process?
No, the key with friction stir welding is really to the mating surfaces, twist and bow, straightness, flatness comes into play. There's friction stir welding. The technology has advanced over the years. There's more and more suppliers out there providing those services. And I've seen a lot of very complex profiles and various alloys that have efficiently and effectively been friction stir welded. Some of what I've seen in the past is the utilization of fixtures, both in the fabrication, the machining portion, also being utilized in the friction stir welding. So once the parts are machined, they're also friction stir welded in the same restrained state. But a very effective process. Mm-hmm.
Are there any design guides available for complex multi-void extrusions? We're talking about wall thicknesses, expected tolerances on internal walls, what kind of fully internal geometry is reasonable, et cetera. It might depend on, I guess the purpose.
Yeah, I've been in this industry for a little over 32 years, and that's probably the most asked question I always receive. But there is so many things that are taken into consideration. So for example, internal wall thicknesses, there's often the question of what is the minimum wall thickness of an internal wall. Some of the things that come into consideration just with that question is the chemistry the homogenization, as we talked about, the type of press it's being extruded on, the length of the wall, the material flow path relative to feeding that wall, can all have an impact relative to a certain wall thickness. There are general guidelines, but I've found that they're so generic that there's not a tremendous amount of value there. And in some cases, I feel that it restrains the ability for an engineer to develop a design that's going to be most effective. The comment or the way that I've always liked to approach it is, what's the most effective, has the most value, provides you the solution that you're looking for, provide that to your extruder, and let them provide feedback relative to it. And not only can they give you the feedback relative to what can or can't be done, but it can be a learning process as well of trying to understand, why is that the case?
Awesome. Well, hey, thank you so much for the presentation. I want to be cognizant of everyone's time. So if there are questions, or if there might be a couple questions or comments we didn't quite get to, I will forward those to Mark and can follow up offline with you directly. You can reach out to him directly here. His contact information is on the screen. So I want to thank Mark for his presentation today. I want to thank AEC for their membership with Lift. I want to thank everyone for joining us today. Certainly appreciate it. And stay tuned. Reach out to Lift with any additional questions about our organization or membership therein. Stay tuned to your emails. I think we're taking the rest of July off, and I think the month of August off as folks are on vacations and enjoying their summers. Here's the webinars. So we'll gin these back up in September. But in the meantime, Mark, thank you. Lynn and the AEC, thank you so much for everything you do here with Lift, and thanks everyone for joining. We'll talk to you next time.
Thank you.